So thank you very much for the invitation to the organizers and for putting together this wonderful event. I would like to wish happy 50th birthday to the AWM. And I look forward to hopefully also participating in the in-person part of this conference next year. So, right, let me start my talk with a little bit of an overview of what this project is about, which is joint work with Tony Licata, Ivan Losev, and Yacobi. And my talk will have both algebra and combinatorics. I'll start first with the algebra, or the more category theory perspective, and I will talk more about the combinatorics a little bit later on. So here's an overview of this project, and we'll assume that G is a simply laced Kac-Moody Lie algebra, so type ADE. If you prefer, you can think about SLN, so just the traceless n by n matrices with the commutator Lie bracket. So given such a Lie algebra, one can think about the quantum group, so the deformation by parameter Q of its universal enveloping algebra and representations for that quantum group. So this is this category of representations of the quantum group of G. And this will be a very big picture story, which I will elaborate on in the future slides. So given that, there's so work of Kashiwara, who said that given a representation for the quantum group, you can consider the special case where the quantum parameter goes to 0. And in that setting, you get a combinatorial shadow of such a representation called the crystal. So this is where the combinatorics comes in, where we have nice directed colored graphs, which capture a lot of the information coming from the representation. Now, for a representation to complete this square, let me mention that work of Lusztig showed that given such a vector space with an action of the quantum group, there's also another type of symmetry it carries, namely an action of the Braid group of the corresponding type. So this gives us a Braid group action through Lustig's work on quantum group representation. Now, in joint work with Kamnitzer, Rybnikov, and Weeks, we show that there's an analogous action on the combinatorial end, so on the side of crystals, given by a group closely related to the Braid group called the cactus group. So for any crystal, we can realize an action of the cactus group on that crystal. So this is the classical story of representations in crystals. So the higher version, categorical story, is what happens over here. So work of Kovanov, Lauda, and Chuang-Rouquier has described how to construct for each representation a category which has some higher information and carries an action of the quantum group. From here, by taking the Grothendieck group, we can recover the original representation. There's also a way to go directly from such a categorical representation to the combinatorial data of a crystal. And furthermore, so there's a way to get a categorical Braid group action, which is mainly what this project is about. By work of Chuang-Rouquier and Cautis-Kamnitzer, through functors called Rickard complexes. So given the categorical quantum group representation, you can get a categorical Braid group action on it. And again, taking the Grothendieck group, you recover the Braid group, original Braid group action. And so what we do in our work is complete this arrow. So going from the categorical story of a Braid group action, there is a way to recover the combinatorial symmetry from the cactus group using a technical tool called perverse equivalences. So this is the big picture. Let me start now from the beginning and give some more details. So what is the categorical action of a Lie algebra? So here's the warm-up setting where we start with the just traceless 2x2 matrices, SL2. So this Lie algebra has basis E, F, and H, where E is just this matrix, F is the matrix with 1 in the bottom corner, and H is the traceless diagonal matrix. So this Lie algebra can act on a given representation for it, which decomposes into weight spaces. And these elements, E, F, and H, so E raises the weight by 2, F lowers the weight by 2, and they satisfy a particularly nice relation on the nth weight space, which is just given by n times the identity. So it just acts by a scalar. Now, what is the categorical version of this? So to get a categorical action, one upgrades the vector space to a category. For our purposes, is going to be an abelian category, together with a collection of weight categories. There's the operators E and F get upgraded to endo-functors on this category, which again have the same property as the original operators. And the interesting structure that one gets in addition to what we had just on looking at vector spaces with the action of the Lie algebra is this higher structure coming from the natural transformations. So rather than having just an equality for such a relation, there's some higher data of natural transformations between these functors, which give us an isomorphism for such a relation. So let me show you on the next slide. So these natural transformations I mentioned earlier, they give us an isomorphism rather than an equality. And moreover, they produce some interesting symmetries on the powers of the raising functors. So the powers of the functor E carry an action of the nil-affine Hecke algebra. So this is another diagrammatic algebra that has a very nice presentation, and we can see that extra structure on the categorical level. So this is one motivation to think about this higher level. For instance, if we think about the adjoint representation of SL2, so this is SL2 acting on itself using the Lie bracket. This is a three-dimensional representation. And so the weight spaces have weight 2, 0, and -2. And so on the categorical level, we replace each weight space with the following categories. So just vector spaces for the highest and lowest ones. And the middle one is just given by modules for this ring. And the functors between them are just the induction and restriction functors. So there's a very nice concrete way to realize this representation. Now, more generally, beyond the SL2 story, one can do something very similar, where one way to describe this or to capture this information is by looking at a 2 category, which generalizes the universal enveloping algebra. The objects in there are the weights. The one morphisms are generated by the functors E and F, where we have more than one pair here because we're working in the more general G setting. And the 2 morphisms, so this is similar to the story we saw with the nil-affine Hecke algebra for SL2. They have a diagrammatic interpretation where the relations between them can be captured very intuitively using such diagrams and stacking them and putting them together in a prescribed way. So this gives us the Kuvanov-Lauda-Rouquier algebra, giving this higher structure. And then when we think about representation from this point of view, this is going to be a 2 functor from this category to some other appropriate 2 category. And if you want to think about the quantum group, then one can consider a graded version of this 2 category, and that grading captures the quantum parameter Q. Okay, so now that we have the categorical picture in mind, let me mention these Rickard complexes which realize the Braid group action I was talking about on the first slide. So starting again with the SL2 picture, consider this element, which is a lift of the simple transposition in the Weyl group for SL2. So the Weyl group for SL2 is just the symmetric group on 2 elements. And the generator for that is the simple transposition. So this is a lift of that, and it can be expressed using the raising and lowering Chevrolet operators in this way. So this expression is quite complicated in general, but one can get a much simpler form of it when we restrict to a particular weight space for a given SL2 representation. So restricted to a particular weight space, this operator is an isomorphism, and it has this explicit description. So then one can ask about what is the categorical version of that? What is the higher level version of such an operator? And so the answer is the Rickard complex. This is a complex of functors where each of these functors goes from complexes with objects in the category C, or the corresponding weight categories, and is given by the following complex. So we have powers of the Chevrolet functors E and F, where this is the part that lives in homological degree 0, where each of these functors is defined using the nil affine Hecke algebra action, and the differentials between them come from adjunction. So from these natural transformations that we saw earlier. Okay, so given this Rickard complex, which generalizes that operator in SL2 we saw, this further induces a self-equivalence on the bounded derived category. So having an even more interesting structure on this category C through work of Chuang and Rouquier. And this, going back using the Grothendieck group, going back to the classical level, the non-categorical level, it recovers that element S that we saw. And for instance, going back to the SL2 adjoint representation, on the 0 weight level, what this functor does is, so take a module for this ring R and maps it to the complex where it has 2 components. One of them is just the module itself, and the other one is the ring tensored with the module, with the differential given by how the ring acts on N. So this is an example of what this functor does in that case. So a little bit more algebra before I go into the combinatorics. Let me explain this property that we're interested in for the functor for this Rickard complex theta. So the property that we wanted to satisfy is so-called perverse equivalence. And this is defined for a functor of this type, where A and A prime are abelian categories with the extra information that we have filtrations on each of them, as well as a function from the indexing set of the filtration to the integers called the perversity function. So such a functor is said to be perverse with respect to this information, the 2 filtrations and the perversity function, if it satisfies the following 2 properties. So F up to a certain shift restricts to an equivalence on the categories where the cohomology lives in that particular filtered piece. So restricting to the cohomology living in AI or AI prime respectively, that gives us an equivalence. And then when we take the quotients, there's an induced equivalence there, which restricts to an equivalence on the hearts of these categories, namely on the underlying quotients of the AI mod AI minus 1. So this is what the perverse equivalence looks like. And indeed, Rickard complexes satisfy this property. So what I need to tell you is for a given category endowed with an SL2 action, what are the two filtrations and what is the perversity function? So the filtrations are very intuitive. We can put one filtration based on what power of F kills an object here, and another filtration, which is given by what power of E kills an object here, where we're restricting our attention to the simple objects. So these two types of filtrations, together with the identity function, give this Rickard complex the structure of a perverse equivalence. And moreover, we can, so for a given reduced word in the Weyl group, we can build a complex for that out of complexes for each of the individual elements. And we show, so this is in the work of Chuang-Rouquier, where they show that perversity holds for SL2. More generally, we show that for the longest Weyl group element, the corresponding Rickard complex is also a perverse equivalence. So it satisfies this technical condition. Maybe let me mention briefly what goes into the proof. And I will get into a little bit more combinatorics after that. So just briefly, I don't want to spend too much time on this slide. The idea is that we use a Jordan-Hölder filtration on this category C, where each component here is a subrepresentation and their quotients are given by reducible representations. And moreover, the perversity function is given by a certain consideration based on the highest weights that appear in the quotients here. Okay, so just some ideas of the construction. It's not too important for what I'm about to say next. So let me move on. So, okay, this was the algebra side of the story. Let me say a little bit about where the combinatorics comes in. So I mentioned some braid group actions and cactus group actions at the very beginning. Let me remind you, if I here denotes the Dynkin diagram of the Lie algebra we're considering, then we can define the braid group for that type as the group with generators indexed by the Dynkin diagram nodes, and the two types of relations, because remember, we're in the simply laced case, only type ADE. So they commute if the two nodes in the Dynkin diagram are unconnected. And we have this braiding relation whenever I and J are connected by a single edge. So that's what the braid group looks like. Now the cactus group is generated not by individual Dynkin nodes, but by connected subdiagrams. So connected graphs within I. So for instance, in SL5 here, this is what the Dynkin diagram looks like. And then we'll be considering each connected component of that. So this is what the J's look like. And there are three types of relations. These are all involutions. They commute whenever the two subgraphs are far apart from each other. And there is a certain skew commutativity when one graph is contained inside the other. So if K lives in J, for instance, this could be K and this whole thing could be J. This purple picture, then trying to commute K past, J past K, whoops. What we get is that the smaller component gets reflected within the bigger one. So this is where K goes under this reflection. So there's some very explicit relations which give us the relations for the cactus group in terms of the symmetries of the Dynkin diagram. Now, going back to the Rickard complexes, these functors that I described, Cautis and Kamnitzer show that indeed they satisfy these Braid relations. So how can we use that? Let me mention a few more words about the Braid and cactus group before I get back into the algebra of the Rickard complexes. So the Braid group surjects onto the symmetric group, where the kernel has a nice geometric interpretation given by the fundamental group of a certain configuration space. And similarly, the cactus group surjects onto the symmetric group, where the kernel is the fundamental group of a certain interesting space. And this is where the name cactus comes from. So for instance, in the case n equals to 4, this space is one-dimensional with its cells labeled by these cacti, curves with marked and labeled points, which are the needles of the cactus here. Okay, so since I'm running out of time, let me now mention what is the action of the cactus group, which we're thinking about on the higher level. So the cactus group CG acts on any crystal of type G by breaking up the crystal into the irreducible components and then looking at what happens on each of these irreducible components. So the map for the cactus commutes in a certain way with the operators for the crystal, and it has a nice interpretation in terms of the weight as well. So let me show you a picture of how this works for the SL3 crystal for the adjoint representation. This is what the crystal looks like. So it's a nice colored or oriented graph. And for instance, the element of the cactus group labeled C12 swaps the highest and lowest elements and then permutes the other ones in a way prescribed by those relations I described earlier. So there's a very concrete way to realize this. And so going back to the original big story, so in the last slide, we saw how a cactus acts on a crystal. And now to recover this action from the categorical point of view, using perverse equivalences, we show that these Rickard complexes induce bijections on the simple objects of the category C. And in fact, these bijections are exactly the cactus bijections that we saw in the graph picture. Okay, I'll stop here and thank you for your time.